All right. Welcome back, everybody. Let me just make sure that yeah, it looks like we're recording here. Okay, cool. So yeah, session 2, once again, we're going to be hearing from John Stevens, CEO at Veridise. Today, we're going to be focusing on ZK security considerations. So we had smart contracts, and now we're going to focus on ZK. So thanks for joining us, John. I'll hand it over to you.
Thanks. Okay, let me share my screen. Okay, can you see this?
Yep.
All right, today we're going to be talking about ZK security. So overall, the talk today is going to be somewhat similar to the talk yesterday, in that first we're going to look at, kind of the security model that we have when it comes to ZK circuits and some important security considerations. Then we're going to be looking at, kind of common bugs that we see in ZK circuits, many of which cause under-constrained circuits. But again, we'll look through some common issues that we see. And then, because many of you are in Web3, or because I gave a talk about smart contract security, I assume many of you are going to be creating ZK circuits for Web3 applications. So after that, I'm going to go through some of the security considerations that you have when looking at the combination of smart contracts and ZK. And then finally, similar to yesterday, we're going to go over, some of the things that you can do in order to help catch these bugs early. Okay, so the first thing that we're going to look at is, bugs in ZK circuits. So the structure of this is going to be somewhat similar to yesterday, but unlike yesterday where we kind of had these case studies, because ZK is so new, and for some other reasons which we'll probably see later, we don't really have these kind of case studies for ZK because there haven't been these kind of notable hacks. That's partially due to like I said, ZK being so new, but also kind of due to ZK itself, where it's harder to identify a hack just because of the nature of these ZK circuits. But we'll take a look at that in more depth later on in this talk. So the first thing that we're going to do is we're going to look at, kind of the workflow of a ZK circuit. And what I mean by that is when you have a ZK circuit, you're going to start with some, source code that is going to be compiled. And when it's compiled, you're going to get two things. You're going to get the witness generator, which is the piece of code that you have that generates the witness, which is fed to the prover. And the prover is then what generates the proof, which ultimately is provided to your verifier. And that verifier may be on-chain or it may be somewhere else. So you're going to get your witness generator, which generates that witness, as well as a set of polynomial field equations. And so these are the equations that are used in order to, check the validity of the witness in the verifier and in the prover. And so from those polynomial field equations, like I said, you get, kind of this prover, which is customized towards those polynomial or those equations that you have, as well as the verifier. So if we take a look at a common programming language like Circom, which is a very common ZK DSL, you might see a circuit like this, where you just have an example circuit. And I believe that you guys already took a look at the high-level structure of Circom, so I'll go through this a little bit quickly. But as you guys already probably know, there are several different operators that perform kind of similar assignment-y operations. So one is this, kind of single arrow operator. Another is the double arrow operator. And then finally, you have a unique constraint operator. And each one of those does something slightly different. And so it's useful just to make sure we're on the same page by establishing what effects that has on the ZK circuit, or on, the lower level representation of the ZK circuit. So basically what happens is if you have a single arrow assignment or a double arrow assignment, or the double equal assignment, then you're going to end up performing that assignment in the computation. However, you'll notice that not all of those are going to go into the constraints. And so not all the operations that we have here are going to end up being in your polynomial fields. So more specifically, you can see that assignments performed with a single arrow do not end up in this constraint, whereas the triple equal sign or the arrow with the double equal sign end up being added as constraints. And so this is important because of, kind of the flow that we have of a ZK circuit, because as we already talked about, inputs are going to go through this computation portion, which is the witness generator, that's going to generate a witness, and then that witness is going to be checked with your constraints in the prover, and ultimately that will generate a proof. So one thing that we've noticed while auditing these ZK circuits is it is commonly the case that developers want their computation and constraints to be equivalent. And what I mean by that is essentially, I think I talk about it here. What I mean by that is essentially if you have a program, this is your witness generator that takes as input X and generates outputs Y, then essentially you want to have this kind of relationship where for every input-output example that you have, or for every input and output from that witness generator, you want to make sure that your constraints can only accept those inputs and outputs. But you also want the same in reverse, which means that if your constraints are going to accept a set of inputs and outputs, you want to make sure that those are the outputs that would be provided by your witness generator given that set of inputs. And so essentially you want to make sure that your constraints can only accept output or witnesses from your specific witness generator. And you want to make sure that your witness generator will only produce witnesses that can be accepted by your constraints. And so basically every input and output example must be accepted by C, and every input and output which is accepted by C must be produced by P. So fairly simple. However, what we're going to be looking at more specifically is how this can be violated. So now I'm going to go back and just talk a little bit about why we care. And so the reason why we care about this is not necessarily because we've seen gigantic hacks in the past. It's more because there are indications of mistakes that people have already made, which luckily have not led to significant vulnerabilities because they've basically been caught before an attacker was able to find them. So specifically, Tornado Cache had a bug in their code which would have allowed an attacker to drain their entire pool without, having to actually put funds into the pool. And luckily they found that and they exploited it themselves in order to, rescue funds and then deploy a fixed version of their pool of tokens. There have been some other cases that we've seen as well where, like in Aztec, there was a potential for a double spend vulnerability that was discovered and disclosed and fixed before release. And same in Circom lib, where we've seen cases where math could be performed inaccurately. And it's hard to tell what the actual impact of that would be because it would be very application specific. And so all of these have been found before, ZK circuits made it into production. And so the reason why we care about these problems is because we've seen mistakes happen. So far, they've luckily been caught. But as ZK circuits become more ubiquitous, it's likely that more of these errors will not be caught. And some of them will be difficult to find due to the nature of ZK. So for example, if we have private inputs that we're operating over frequently, it might be difficult for someone to tell that someone was able to mint an infinite amount of funds. You really have to tell by, side effects that happen. And so we can talk about that a little bit later if you want, but detecting when an exploit has occurred in a ZK circuit is going to be more difficult than with blockchain applications just because everything is public in blockchain applications, and that's not the case with ZK circuits. That's kind of the high level here. Okay, so when we're looking at bugs in ZK circuits, we kind of can organize them into this taxonomy. And so specifically, some of the types of bugs that we've seen frequently are completely unconstrained signals, constraint computation discrepancies, unsafe component usages, and logical errors. So logical errors is going to look very similar to what we visited yesterday, and we'll go over a little bit more about what they look like in ZK circuits. But as for these other types of vulnerabilities, there are a lot of different ways in which they can occur in ZK circuits. And so really what we're going to do is we're going to describe the class of vulnerability, and then we're going to look at specific instances which show, kind of how that class can occur. So let's go ahead and take a look at our first class. And so that is unconstrained signals. And so a lot of the side effects of some of the classes that we saw previously is the circuit would become underconstrained if that particular class of vulnerability was in the ZK circuit. An unconstrained signal, though, is a type of underconstrained circuit where a signal is completely unconstrained, which means it always evaluates to true, or it can always evaluate to true. And so that means that the circuit or that particular signal is going to accept any value. So there's a couple of ways that these can occur, and we're just going to take a look at one fairly simple one. And so one example that you can see is here you have a template. That template is going to add 2 arrays of values and presumably accumulate them in this output array. However, the person, rather than iterating up to n, they only iterated up to n-1, which means that the last index of out is not constrained, and therefore the last index of out can take on any particular value. It does not have to be the sum of a and b, and as a result, bad things can happen where that particular value could accidentally be used, and if it was, then basically anything could be assigned to that particular output. Okay, so the next class that we're going to look at is unsafe component usages. And so what an unsafe component usage corresponds to is oftentimes when we use templates that are provided by libraries, there are kind of assumptions that go along with those templates. So as an example, like less than and greater than, the comparator operators that you have in Circom lib, it assumes that you're going to, 1, ensure that the inputs are constrained, and 2, you're also going to check that the output value is equal to 1 or 0. So when you call the less than, or when you invoke the less than or greater than template, it's not automatically going to check that this particular thing is unconstrained. It's up to the user to place a constraint on the output value, which is something that sometimes people don't expect. And so this is what I mean by subcircuits often have assumptions about how the inputs and outputs are going to be used. And so these unsafe component usages correspond to cases where people do not use these subcircuits correctly. And so there are, again, certain instances that we can look at of this where there are many different types of ways where people can use a circuit incorrectly, but we're just going to look at one. And this is going to specifically correspond to the bug that I mentioned earlier. So if we look at this particular circuit, it seems like it's trying to allow someone to privately withdraw money from a pool. And so it's going to take as input a balance, the amount that they want to withdraw, and some output. And you can see here that there's this less than comparison where they seem to be trying to check that the balance, or that the amount that is passed in, is less than the balance, or something along those lines. However, in this case, they're missing a constraint where they should actually be checking that the output of less than is 0, because they're just trying to make sure that balance is greater than or equal to the amount. And so they're using less than as greater than or equal to here. And as a result, they need to constrain the output of less than to be 0. And because that's missing, they're not actually enforcing this relationship between input variables. And as a result, someone could theoretically withdraw more funds than they have or in their balance. And as the other kind of side effect of this is, if you consider output here, because Circom and many ZK languages don't actually enforce that fields cannot overflow or underflow, that subtraction down at the end could also underflow, which would result in that output value being a large value at the end of this, which is similar to other vulnerabilities that we've seen in blockchain applications in the past. So without that missing constraint, essentially the attacker can withdraw more funds than they actually have. And this is where, this type of vulnerability can have a significant impact on applications. The next type of vulnerability that we're going to look at is constraint computation discrepancies. And so here, essentially, what I'm talking about is we saw that there are these single arrow operators. And the reason why they have to be included in the Circom language is because Circom doesn't allow you to express constraints unless it's in this kind of QAP form, which means that the constraint has to be representable as a quadratic formula. And if it isn't quadratic, then Circom is essentially going to reject the constraint. And because you can only really include multiplication and addition in a quadratic constraint, it means that there are certain types of operations that can't actually be represented directly in the constraint form acceptable by Circom. And so users have to use this single arrow assignment sometimes, and then they have to model what operation that performs using the typical QAP, the acceptable form that constraints can express. And so really what this constraint computation discrepancy corresponds to is a case where constraints do not actually capture the semantics of the computation correctly. And so again, there are many ways that this can occur, and we're just going to look at a specific one, which is divide by 0. So more specifically, what's going to happen in this case is, let's say someone has a divide template. And so that divide template is obviously just going to divide the inputs, and it's going to put the value in the output. And so for those of you who aren't familiar with this, just in case, rather than using the typical slash for divide, you have to use the opposite slash, the what is that, forward slash, I think, because the other slash is used to represent the multiplicative inverse. However, when you are using this particular division operation, you also can end up having an issue where the modeling of the operation is not performed correctly as constraints. So if we take a look at this, essentially we know that division is undefined when the denominator is equal to 0. However, this isn't something that is actually considered when you look at the constraints. And so as an example, if b ended up being 0, then what would happen in the witness generator is it would throw an error. It wouldn't let someone run the witness program using that as an input. However, just because your witness generator failed to generate a witness doesn't mean that someone else can't go and generate an alternate witness from some other witness generator and provide that to your prover. And so if someone were to do that, they could, construct a witness where b is equal to 0 and provide that to the prover, and the prover would happily accept it because, the constraints are still satisfied. However, one thing that you'll notice is when when b is 0, then as long as a is 0, out can be anything, which means that what someone can do here is they can, pass in 0 as a, 0 as b, and then they have full control over out. And so that can be fairly bad because, depending on what your application does, you assume that, when you're performing a division, you're going to get something consistent with division in the output. But unless you are actually modeling the computation correctly, which can be difficult, oftentimes we don't think about the case where the denominator is 0. You're not actually going to be checking the things that you want to be inside of your constraints. And so you have to be very careful when your constraints and your computation diverge. And so this is kind of what this is talking about. And we've seen this happen in multiple applications, specifically with division. We've also seen it happen with when people use the multiplicative inverse operation. And then another one that's fairly common is there are cases where people use the ternary operator on a signal, and in that case, things can get bad as well. So it's, again, always better to use the double arrow assignment. That way, everything that you encode inside of your computation is also encoded in your constraints. But when you can't, just make sure that you look at that particular formula a lot and make sure that you can convince yourself as well as other people that you are actually encoding the computation correctly as constraints. Okay, so the last particular type of common vulnerability in ZK circuits that we're going to look at are logic errors. And so logic errors, similar to what we saw yesterday, are kind of violations of the business logic specification. So what we saw yesterday is there were two types of violations where one or both of them kind of correspond to violations of this implicit specification, but sometimes it's because someone doesn't implement behavior that they assume will hold, and other times it's because they implement behavior incorrectly. We see the same thing in ZK circuits. So one particular case that we consider is this field overflow. And so we've seen this happen in a number of applications as well, where people assume because they're used to using languages like Rust, which will check for overflows as long as you don't turn that off, as well as Solidity, which ever since Solidity 0.8 has checked overflows and underflows by default. People sometimes assume that they have the same behaviors in this ZK circuit domain. However, that's not the case. Circom won't check and doesn't add constraints by default to prevent these overflows and underflows. And so if there happens to be something that will overflow or underflow a field, Circom will happily allow that to happen. And so that means that you need to add in additional constraints in order to ensure that doesn't happen. And so in this particular case, if we have this template, which is trying to represent a transfer of funds between two users, that can be particularly bad because, as we saw in the early days of Solidity, someone could always underflow their balance in order to get an extremely large balance. And that's what could happen here. And so really what someone needs to do in this case is they need to add in either constraints on the values of the balances or the amounts that are provided, or they need to add in some additional logic to prevent from overflows and underflows. Similar to kind of like safe math that was implemented in Solidity. Okay, so those are the common vulnerabilities that we're going to, or that I had planned to look at in the ZK circuit side of things. So you'll notice that it's shorter than what we saw yesterday when we were looking at smart contracts, and that's kind of for two reasons. One, because this is a new domain, and so new bugs might pop up, particularly as new languages are created, but also because the execution environment of a ZK circuit is easier. It's more constrained. It's not quite as open to other users. And what I mean by that is, if you look at smart contracts, you have things that you have to worry about, like storage and the environment and stuff like that. Whereas with ZK circuits, really everything that you have to consider is contained within the circuit itself, because you've got inputs that you need to verify and outputs that you need to compute. So what we're going to look at next is going to be issues that we've seen when people have ZK circuits and DeFi applications interact. And so more specifically, what we need to consider is the differences between a ZK circuit and a smart contract. So implicitly, circuits are stateless. While there are languages that attempt to add states to ZK, these are languages that kind of mix blockchain applications with ZK circuits. These circuits themselves are stateless, and someone has to go and try to add a way for circuits to reason about states. This is usually by having circuits reason about, Merkle trees, and then having additional checks outside of the circuit to make sure that, it was reasoning about the correct Merkle tree. And so, but still, ZK circuits themselves are stateless, while as smart contracts have persistent storage. In addition, ZK circuits typically have restricted control flow. This is because, as you guys will have seen when working with languages like Circom, it is a ZK circuit needs to make sure that when the circuit is compiled, all of the code is straight line, which is why you typically don't or are constrained on how you can add conditionals into ZK circuits and on the types of loops that you can perform in ZK circuits. This is because you need to make sure that at the end you can get this, single piece of straight line code. Smart contracts, however, allow arbitrary control flow, and as we saw yesterday, control can even transfer to other contracts, whereas in ZK circuits, you can't transfer control to another circuit. The other thing about ZK circuits is they're operating on finite fields, which, as you guys know, is going to be restricted by some typically very large prime, whereas smart contracts work on some sort of big integer. In Solidity, this is a 256-bit integer. And finally, ZK circuits are allowed to operate on public or private data, whereas smart contracts, mostly there are ways to hide values now, but in general, smart contracts work on public data. And this is because people have to, generally see the data to know how they can update the state of a smart contract. Okay, so when ZK circuits and smart contracts interact, basically what happens is you have a user who's going to interact with the ZK circuit. That will ultimately generate a proof, and that proof is going to be verified on-chain. And once it's verified on-chain, presumably the state of the blockchain is going to change somehow. And so we can take a look at how this looks or how this works in a couple of different environments. And so the ones that we're going to look at specifically today are Solidity and Circom, Leo, and O1JS. And the reason why we're going to look at these is because, each of them kind of has a different way of allowing smart contracts and ZK to interact, where in Solidity, you're basically required to write the ZK circuit yourself and, plug it into your smart contract very explicitly. Leo and O1JS try to allow you to do, kind of both at the same time. However, even though they are allowing you to write these kind of ZK applications in line with your smart contract code, the overall flow that we looked at earlier still remains the same, where, essentially they have an off-chain component that has to, actually run the ZK circuit, particularly when there are private inputs, and an on-chain portion which will, perform state updates and stuff like that. And so we can take a look at the similarities and differences and see how, kind of these vulnerabilities that, or these ZK DeFi vulnerabilities appear and compare in different ecosystems. And so that's what we're going to be doing. So I'm first going to go and look over, some properties of each of these ecosystems. So in Solidity and Circom, the storage type is big int, whereas in the other two ecosystems that we're going to look at, they allow a mixture of finite fields and big ints to operate in the actual smart contract code. In Solidity and Circom, the smart contract control flow is more or less arbitrary, whereas there are restrictions that are placed in Leo and O1JS. The reason why I say this is because, while some smart contract code can be arbitrarily performed, if that code is going to be encoded into a ZK circuit somehow, they have restrictions, the same kind of restrictions that we see in Circom of the type of control flow that's available. Then if we look at the logic separation, this means that, where is the ZK circuit written versus the smart contract written? Solidity and Circom obviously is going to be separated because you have to write your Circom circuit separate from your Solidity contracts. Leo, they're also separated where previously they had this notion of a transition and it was, let me remind myself of what they actually called those. The transition function and the finalize function. These slides are a little bit old, and Leo has now transitioned to, rather than using that terminology, they are now, emitting futures that you're going to be waiting on in the ZK circuit, but that kind of confuses things a little bit here, where it makes it a little bit more difficult to tell exactly what goes in the ZK portion of the code versus the smart contract portion of the code. So we're just going to take a look at the old version where they had this very explicit separation, just because it's very easy to say the transition function is going to be your ZK circuit, and the finalize function is going to be your on-chain contract, the thing that's actually going to update state. When it comes to the future version that they have now, I believe both of those are called either functions or transitions or something like that. And it just makes it a little bit more difficult for me to explain what goes where. Anyway, it's not a big deal. The language still looks very similar, other than the futures. Finally, in O1.js, the smart contract code and the ZK code are in line, which means that you're writing everything in one piece of code. And we'll take a look at what that looks like in a little bit. Finally, the last comparison that I want to perform is on proof verification. So this is exactly how a ZK proof is going to be verified on chain. So in Solidity and Circom, you have explicit proof verification, which means that when someone generates a ZK proof, they have to explicitly pass it into a smart contract. And that smart contract has to very explicitly verify that or check that the proof verifies. In Leo, this is done implicitly, whereas previously I mentioned this transition function and finalize function. The Leo blockchain will implicitly verify the ZK circuit that corresponds to the transition function when executing the finalize function. And so the user doesn't actually have to do that. In O1.js, we actually see a mix of both, where depending on how someone writes their ZK circuit, they can either have that circuit be implicitly or explicitly verified. And again, this is something that will come up again in the future. So the first particular type of error that we're going to look at is missing state validation. And so what missing state validation is going to do, or what it corresponds to, is because a ZK circuit is stateless, when someone wants to interact with state in a ZK circuit, they have to explicitly pass that state into the circuit itself. So essentially, in this particular case, a user wants to pass some state into the circuit, and they might say that the value of that state is 0. The ZK circuit will happily compute because it doesn't actually know the on-chain state unless that's somehow passed into the circuit. But if you're writing these yourself in Circom, it typically doesn't know. And then when that state is verified on-chain, you actually have to make sure that the on-chain state is still consistent with the state that was passed into the ZK circuit. And what I mean by that is, by the time the ZK circuit has finished, generating the witness and proving, it could be the case that the state on-chain has changed already, or it could be the case that the user just passed in the wrong state. And so when you are verifying your ZK circuits on chain, you have to make sure that arguments that correspond to state or some aggregation of state is actually correct. And so we can see what that would look like here. And so I'm showing you 3 different versions of essentially the same code. And so that code is going to transfer value more or less privately. And so in Solidity and Circom, this is done by having the Circom, or by using the Circom template on top and the Solidity function on bottom. In Leo, I talked about the transition function and the finalize function, where the transition function is going to correspond to your ZK circuit. Your finalize function is going to correspond to what happens on chain. And then finally, in O1.js, there's this kind of mix, which I talked about previously. And in this mix, essentially what happens is certain operations that you perform in O1.js are going to be performed in a circuit, and they're going to be generated in constraints, whereas other operations are not going to do that. So if we look at the same bug across these 3 languages, we can see some commonalities where state transitions are not verified correctly. So in particular, let's take a look at the Circom and Solidity example first, because that is probably what is most familiar to you guys. So what happens here is a user is going to be expected to provide, the balance of the person that is transferring the tokens and the balance of the person that the tokens are being transferred to. And then it is going to compute those outputs, and then the proof of that computation is going to be provided on chain. However, what you can see here is that when that proof is provided on chain in that transfer function, there is no validation that the inputs to that template or to that circuit are correct. And so because the user, who is not trusted, is going to be the one who's providing those values to the ZK circuit, you don't necessarily know if they're setting them themselves. They're actually, in this case, financially incentivized not to set them correctly. And so what you can see in this case is because they're not being set, the values that, or they're not being checked, the values in the ZK circuit are just being trusted, and therefore are just, adjusting the balances directly. And so this would correspond to a data validation error that we saw yesterday, but it's, a little bit more specific here where, you're missing the validation that the state that people were interacting with in the ZK circuit were correct. And we can see the same thing can happen across multiple languages. So in Leo, similar to what we see in Circom, people can't actually retrieve state from the blockchain. They can only retrieve blockchain state inside of that finalize function. And so as a result, you can see in the transition function, similar to the Circom template, they're trusting someone to pass in the correct value of the balances. And then in the finalize function, they should be checking to make sure those balances are correct, but they aren't. And then finally, in the O1JS example, you can see that, it is similar where it's having someone, kind of pass in these from and to balances. And, while it is, calculating the roots of the balance tree, it's actually not really checking to make sure that those balances are correct either. This is because you can see that in the calculate root function, it's just trusting the from balance and to balance that are being passed in, and it's not actually validating that those balances are equal to the expected state. Okay, so let's go on and look at another type of error. And so we looked at denial of services yesterday. This is going to be another type of denial of service that is a little bit specific to ZK circuits. And so more specifically, in particular types of applications where the domain of the integers accepted by the ZK circuit and the smart contract do not match, it might be the case that if a value is set incorrectly in the smart contract, it means the ZK circuit might be broken. So more specifically, you can see here that a user is setting a value to uint max, and then they're trying to prove some information about that value in the ZK circuit. But in that ZK circuit, operations are performed over a finite field. And that finite field might not actually be able to represent the value of uint max. And so we see this using in Circom because the default prime is only able to represent values up to somewhere in the 254-bit range. And so that means that if a value could possibly be set to a value or any particular value above the prime, then now your ZK circuit is broken, and it could mean that your application in general is broken. And so this is specific to Solidity, or the Solidity in Circom, because they are the only example here where someone can specifically choose, or someone is forced to operate over integers of different sizes. So in the Circom circuit, someone is going to operate over finite fields of size 2 to the 254, or somewhere into to the 254. And then in the smart contract, you've got 256-bit integers. So in this particular example, you can see in the constructor, it's allocating funds to essentially the person who constructed the token, and it's allocating them the maximum number of funds. And so in that particular case, this particular token is going to be broken right off the bat because you can't actually prove anything about that value within your ZK circuit. And so when you're working with, this Circom and Solidity combination, you also have to be very careful about how values are being adjusted if you're allowing values to be adjusted only in the Solidity portion of your contract. So if you allow values to be updated on chain, you need to make sure that they are within the range of the prime that is being used within the ZK circuit. And also be aware of what that prime is, because in Circom you can adjust the prime to be a different one. So if you're using Goldilocks, make sure you're checking it against the Goldilocks prime and not the Baby Jub Jub prime. Okay. So another type of, let me see what this is. Okay. So another type of denial of service that we see is, kind of a control flow denial of service. And so this is another type of denial of service which is related to the previous arithmetic denial of service. And really, I probably should have renamed this to something else, but it is still related. It's just you don't have control flow to avoid errors. And so because of that, you can have cases where your ZK circuit should try to avoid an error, but it can't. And so certain arithmetic errors might occur if you check them within the ZK circuit itself. And so what I mean by that is, let's consider the Leo and O1JS case right here. And so basically what's going to happen in this particular case is in Leo and O1JS, you have the ZK circuit in line with your smart contract code. However, you have a problem because in both of these cases, you basically need your code to become straight line. And so what would happen in Leo and O1JS is, in the process of trying to, make their code straight line, it's going to be, or there are going to be cases where you would expect, traditional control flow to be able to avoid errors, but it's not actually going to happen. And so this is going to be a very similar, so you basically are going to see similar bugs in Leo and O1JS that you won't necessarily see in Circom. And so more specifically, if you look at the area that I highlighted in Leo, what someone might be trying to do is ensure that a particular value is not going to overflow. And if it would overflow, they're just going to set that value to something else. And so in this case, you can see that they're going to subtract U128 or BAL from U128. And if it is the case that the balance is greater than that value, then they're going to opt to set the value to the max U128 value rather than, actually accumulating the value. So that means that they're going to saturate the addition rather than actually allowing an overflow. However, one thing about Leo and O1JS is they do actually have behaviors to revert if a field, or actually if a U128 is going to overflow. And so what that means is, even though this logic is intended to avoid an overflow, it's not actually going to do so because of how Leo or O1JS is going to, straight line the code or make the code straight line. So it's basically going to calculate both the true case and the else case in that ternary operator. And when it executes it, it's still going to cause the program to revert. So Leo has made some adjustments where you don't need to worry about this in the finalize function, but this can still happen within transition functions in Leo. In O1JS, we see very similar cases where in O1JS, you have to perform anything that you want to be in your ZK circuit in a provable type. And so similar to what we see in the Leo code, they have this provable ternary operator, which is that provable if. And if someone uses that provable if, similar to what we saw in Leo, you can have this arithmetic overflow, which Leo will check, or which O1JS will check for, and will revert if there is actually an overflow. And so this shows how you can get kind of an arithmetic denial of service in different types of languages, where in Solidity you might have to worry about one thing, which is, you know, the domain of your ZK circuit being different from the domain of your smart contract, whereas in Leo and O1JS, you have to worry about something slightly different, which is the restrictions that are placed around control flow causing an arithmetic denial of service, because they aren't actually able to execute the control flow correctly in some cases to avoid errors. And as a result, that can cause certain applications to essentially break. So, you know, same type of bug happens fairly differently. Okay, so I think this is the last type of error that we're going to look at. And let me double check that. Nope, one more. Okay, and that is a finite field overflow. And so what's going to occur with a finite field overflow is, you know, you are going to be operating over a large prime. We already saw this, so I'm going to go over this relatively quickly. And most languages will allow, you know, values to, you know, overflow that large prime and go from being very large to very small. And so in particular, we've found cases where in Circom, even though people, you know, appear to be performing range checks, they don't consider what happens when values accumulate. So more specifically, you might be checking particular values using num to bits, but you aren't checking the range of a particular value, which would allow it to overflow. And so here, more specifically, you can see that the from balance and to balance is being checked. The range of that is being checked using num to bits. However, if you look at, and then the output value is also being checked, but the amount is not. And because the amount can be arbitrarily large, someone can easily overflow or underflow those fields in order to cause some sort of logical error. And in all of the languages that have finite fields, I believe that, and the reason why I say I believe is because I'm not positive about this in O1JS, but I'm pretty sure, is that they do not check overflows and underflows by default in those languages. They do instead have checks on the integer types to make sure that they don't overflow. And so there is a bit of a discrepancy in the semantics that you have in Leo and O1JS, where, you know, depending on the type that you're using, you may or may not have overflow protections. But, you know, that can be good or it can be bad, because we saw cases where overflow protections could cause a denial of service. But in these cases, if you don't consider the fact that finite fields can overflow, you can have other logical errors. Okay. So this next type of attack is fairly important when you're using a language that allows someone to explicitly verify a proof. And so what I mean by that is a proof verification replay attack happens when a user generates a proof, then they go to verify that proof on chain. So they generate they have the proof, and they want to, you know, provide the proof to the blockchain and say, you know, perform some action. However, if that action, or if the blockchain is not properly, you know, performing nullifier checks, or it does not properly compute nullifiers, it might be the case that someone else can take that proof and they can, you know, provide it to the blockchain again and perform an action that the user does not necessarily want to be performed. And so we can see a case where that happens here, where both Solidity and Circom and O1JS allow a user to explicitly verify a proof that comes from a custom ZK circuit. Whereas in Leo, this can't really happen because proofs are implicitly verified. So in particular, you can see right here that there is this transfer circuit that we have been, you know, kind of looking at through this, or a lot of this presentation. And there are appropriate checks to make sure the message sender is correct, the to value is correct, and that the balances of the sender and the recipient are correct. And if all of that is valid, then it's just going to go ahead and verify the proof. In O1JS, this happens very similarly, where In ONJS, you can create a particular type of circuit called a rollup, and that rollup will essentially, separate the ZK logic, similar to what we saw before. And so in the ONJS case, basically what it's doing is it's verifying that the balances that the rollup was operating over was consistent with the current state of the on-chain logic. And if it is, then it's just going to go ahead and verify that proof. The reason why we can end up having an issue here is because basically that proof can be submitted as long as all of the conditions that are outlined here are met. And so in the Solidity and Circom case, that means that, the message sender matches, the recipient matches, and the balances match. And in the ONJS case, it means that all of the balances are equal to what was computed in that particular proof. The reason why this is an issue is because this particular ZK circuit can be submitted multiple times. I mean, these constraints are not unique to this one situation. And so more specifically, if it's ever the case that the message sender and the recipient have that balance in the future, then someone can just replay the proof in order to transfer funds again. And so this is why nullifiers are very important in ZK circuits, because a nullifier basically figures out a way, or it will hopefully create a unique value that corresponds to that ZK circuit, which someone can use in order to ensure that that particular circuit cannot be constructed or cannot be sent in the future. So basically, if someone wanted to transfer funds again, they would have to run the circuit again to compute a new proof. So in this case, typically what someone would do is they would include a nonce, and then using that nonce, they would compute a nullifier. And basically the nullifier would probably include the nonce, the message sender, the message recipient, as well as those balances. And then someone would essentially track when a particular nullifier has been spent in order to make sure it can't be spent again. So this is why nullifiers are very important in this particular, or in this situation where you have ZK circuits interacting with on-chain proofs, or with a smart contract. And it's because you want to make sure that anytime someone sends a proof, it is the case that it can only be spent once. And so as you develop applications, it's very important to reason about whether certain conditions under which a ZK circuit can be verified are unique, or if they might come up again, because it could allow someone to steal funds, assuming you're working on funds, but take some unreasonable action. Okay. So the last thing that we're going to look at is privacy leakages. And so we talked about before how ZK circuits can operate over private and public inputs, whereas smart contracts are pretty much always going to be looking at public values. And that's because values need to be public so that people like validators can go and make sure that that contracts were executed correctly. And so when you're kind of working with this kind of weird ecosystem where once someone ends up posting a ZK circuit, the public inputs as well as the proof become public, you need to start worrying about cases where the ZK circuit might be working on private inputs. And so more specifically, a particular user might expect when they provide a value, like let's say a social security number, that the ZK circuit is going to protect it somehow. However, when someone ends up taking that ZK circuit and providing it on-chain for verification, if it is possible to recover information about the user from that proof, then it can leak information that they might otherwise not want to be leaked. So for example, in the social security example that I just gave, it might be the case that if someone submits multiple proofs, their social security number would be leaked, which would be bad. So we can see a particular case where that can happen here. So again, this is going to be a token, but let's say that someone wants to try to hide the balances that a particular user has. And so in this case, you can assume that the input, so let's see. You can assume that the input value is going to be, or the balance values that are being passed in are going to be private. So you can see in the Circom example that someone is taking the input balance and they are hashing it, and they're taking the output balance and they're hashing that as well. And that is what is being stored on chain. However, in the Solidity and Circom example, you can see that someone is trying to keep track of the total supply, and that total supply is not being hashed. And so because that total supply is public, because it's an output, it is going to be exposed when someone ends up posting this on chain. And because that particular value is exposed, it means that someone can basically calculate the amount that was minted by looking at the difference between the previous total supply and the current total supply. And so the reason why that's bad is because if you assume that the only way people can get tokens is by minting them, you can essentially figure out how many tokens someone has been minted by looking at the differences of the total supply over time in order to, publicly expose people's balances. And we can see the same thing in Leo and O1JS, where again, they also have private values, but the same scenario exists in Leo and O1JS, where public or private information becomes public in some way, and by viewing that public information, they can learn about private information. And so this is an information leak, and it can be pretty bad in ZK circuits. Okay, the last chapter is very similar to the chapter that we looked at yesterday about, how do you identify bugs. So I'm just going to go through this very quickly because you guys have already seen how people can find bugs using different types of tools. And so many of the tools that we're going to look at are from a particular area of computer science called formal methods, which encounters ways of or encompasses ways of reasoning about code. And so in particular, we can see different types of tools that are available for ZK circuits. These include testing tools, static analyzers, and formal verification tools. Right now, fuzzing tools aren't really available for ZK circuits, and so I did not include those in this particular graph. So let's go ahead and look quickly at testing tools. So as we saw yesterday, testing tools essentially are going to, provide a specification. It's going to execute a test by, providing inputs to the ZK circuit, and it's going to check to make sure that it retrieves a specific result. So the problem that we have with testing tools in this particular area is there's a larger class of vulnerabilities that cannot be found by executing tests. And the reason why this is because we know that a ZK circuit is broken down into two things. The first thing would be the witness generator, and the second thing is the constraints, right? Testing tools, however, are going to be executing everything using your witness generator, and because that witness generator inherently adds these, kind of other implicit constraints, you can't actually find under-constrained circuits using traditional testing. The reason why is because you essentially need to create alternate witnesses in order to try to find vulnerable inputs that are not generated by your witness generator, but can be generated by this other witness generator in order to, are also accepted by your constraints. So in order to find these under constrained circuits, you basically need to go through additional work where you define additional witness generators in order to provide adversarial input to your ZK circuit. And so as a result, certain types of vulnerabilities that we looked at today are difficult to find using testing alone, and these include anything that can cause an under-constrained circuit, as well as things like privacy leakages, because a privacy leakage kind of requires that you reason more specifically about source code in order to try to find cases where information can be leaked. So the pros and cons that we have of testing is they don't require any specialty knowledge. They can check custom properties. They don't require any custom tooling because, you know, once you compile your circuit, you can always write tests against it. The cons that we have are they can't detect under constraint circuits. They provide weak guarantees, which we talked about yesterday, and they require some user input because the user has to write those tests. If we look at static analyzers, a static analyzer is going to look very similar to what we saw yesterday. It's going to statically reason about the source code of your ZK circuit. It only requires that you provide your ZK circuit to this particular piece of code, and it's going to spit out issues. The nice thing about static analyzers in this particular case is they can actually find a broader number of the vulnerabilities that we looked at today. This is because certain types of vulnerabilities are more easily, or they can be more easily reasoned about statically. So for example, with privacy leaks, this is something that is well known, or it's well known how to find that using a static analyzer, because you can check a certain property called non-interference, where essentially you just check to see if information can flow from a private input to a public input. And so not all of these checks are going to be perfect. If there is a way to cause an under-constrained circuit that does not fit the vulnerability pattern that is being checked by the static analyzer, then obviously it's not going to be complete. However, what we found at Veridise is static analyzers can, you know, fairly successfully reason about these ZK circuits. So the nice thing about static analyzers are they don't require user knowledge. They don't require user input or specialty knowledge, and they can guarantee the absence of a particular pattern. The cons are they can take a long time to run, and they cannot check custom properties. Similar to what I talked about yesterday, this assumes that we don't have something like semgrep, which could check custom properties and is kind of like a customizable static analyzer. But so far, as far as I'm aware, no one has created a version of semgrep for Circom. Some examples of static analyzers that are available, though, are Circumspect, which was written by Trail of Bits, and at Veridise we have our own static analyzer, which we call ZK Vanguard. So the last things that we're going to look at very quickly are interactive theorem provers and automated verifiers. I separated those for ZK just because those are more, or interactive theorem provers are used more frequently when operating in this domain. And so an interactive theorem prover requires that someone provide the circuit translated to the language of the interactive theorem prover, the specification, and the proof. And the interactive theorem prover is just going to check that proof. So the nice thing about interactive theorem provers is they could theoretically find any of these vulnerabilities. It just depends on how good the person who's generating the proof is and interacting with the interactive theorem prover. But assuming that it's able to verify the proof, then you know, we can basically encode any of these particular properties. They just require a decent amount of work, because not only do you have to specify the problem, you also need to write a proof that shows that your circuit is adheres to that specification or is free of the problem. So the nice things about interactive theorem provers is they can check custom properties and potentially complex properties, and they provide strong guarantees. If you prove that something holds, then it is guaranteed. And then the cons of interactive theorem provers are they require specification. They also require you to translate the circuit to the language that is understood by the interactive theorem prover. They require significant amount of user effort and also typically a significant amount of specialty knowledge on the behalf of the user. But some examples of interactive theorem provers that have been deployed successfully for verifying ZK circuits are Coda, Lean, and Coq. All of those have been used very successfully in order to prove various ZK circuits in this domain. Okay, so the last thing that we're going to look at is automated verifiers. So we looked at these a little bit yesterday. The difference between an interactive theorem prover and an automated verifier is the automated verifier will perform the proof search itself, and so it doesn't require the user to provide the proof. And again, an automated verifier could theoretically, you know, find any of these particular issues. However, you know, it has to perform the search automatically, and so it's not necessarily going to scale in order to do so. So you can find any of those issues, but it doesn't necessarily mean that you can or that it will work. So specifically, an automated verifier can check custom properties. It also has strong guarantees, but they typically require specifications. I'll talk about that in a little bit. And there are no termination guarantees. And this is coming back to what I talked about earlier, where because they are searching for a proof, it might take a long time to find that proof. There is no guarantee that they will ever find that proof. And also, automated verifiers do typically require some specialty knowledge because they might require some user input in order to help guide the verifier as it searches for a proof. Some examples of automated verifiers are Picus and Halo 2 Analyzer. The reason why they have stars next to them is because they do not check arbitrary properties. Instead, they check for a specific class of properties, where both of them look for under-constrained circuits. And so they verify a very specific property. The nice thing is they don't require any user input. But, again, they're not quite as configurable as typical automated verifiers. Magi is another example that I brought up yesterday. The reason why I have it here is because Magi worked on StarkNet code, which is Cairo. And so it also did some, formal verification of ZK circuits. It allowed the user to specify arbitrary properties. However, when we originally wrote Magi, it was for the first version of the Cairo language. And so I don't think that it has been tested after Cairo updated their language to the new, Rusty version. I think it still works because they're using the same bytecode, but I don't know that for sure. Okay, so that's everything that I've got.
Awesome. Thank you so much. Does anybody have any questions? We can go ahead and open it up.
Could you go back to the slide where you were talking about, it was kind of in the beginning, talking about constraint equivalency, and just go over that one more time?
Sure. Okay. So I think you're talking about this slide.
Yeah, I think there might have been one before it too, maybe that I wanted to screenshot, but.
Yeah, no, I think it's this one. We kind of talk about it here, but this is where we introduce the idea of equivalence. So I can explain it here or here.
Yeah,
basically,
okay,
if we take a look at the ZK circuit, so I'm going to go back really quickly. We know that the ZK circuit is going to produce these two things. These are the two arrows that are coming out of that one template. And so that's going to be the computation, which you see on the left, and the constraints, which you see on the right. And so it is often the case that when someone writes a circuit, they have this kind of implicit expectation that the constraints that they encode in their ZK circuit are only going to accept computation that is also encoded within that ZK circuit. And so the reason why this is the case is because typically when people write circuits, they're not, kind of writing general circuits where they expect people to, customize the logic in the future. This is something that you could theoretically do with ZK, but it's kind of dangerous. So for example, with under-constrained values, they are not going to accept a specific deterministic value, which we would typically expect to happen in the traditional programming paradigm. Instead, they can accept any value which meets those constraints. And so this is where the issue lies, where people basically expect that the constraints will only accept this deterministic computation, which they define within that ZK circuit. However, it doesn't. It will accept any computation which meets those constraints. And so that means that if you constrain a value, if we look at, let me show the constraint computation discrepancy really quick. So if we look at this particular value, while it might be the case that the computation is deterministic because you're performing A divided by B, that's deterministic. Anything that, or any set of values which matches or is valid and can be accepted by those constraints is going to be accepted by the ZK circuit. And what I mean by that is the prover is going to generate a proof, and that proof will be verified by the verifier. And so this is where that equivalence comes in, where basically what I'm saying is most developers have the implicit expectation that the constraints that they define are only going to accept that deterministic computation that they encode in their circuit. However, it is a bug when that is not the case. And so this is basically what equivalence is saying, is it is saying that a ZK circuit can be considered to be equivalence if the computation exactly matches the constraints, and the constraints will only verify that computation. And we have an equivalence bug if that is not the case. Does that help?
Yes, thank you.
Okay.
Sounds like that is it. So thank you very much. We can go ahead and wrap it up for today. Really appreciate it, John. This was really great.
All right. Thank you for inviting me, and I hope the rest of this boot camp, goes well.